All right, we might get underway. Thanks, guys. So hello, everyone. Welcome to today's Masterclass presented by Middleton Group on Undertaking Secondary Design, a case study. For those who don't know us too well, haven't attended a talk before, Middleton Group is an Australian-owned and operated specialist electrical engineering organisation working across the power utility, renewable energy, rail, water and heavy industrial sectors. Our organisation has been founded with the sole purpose of working collaboratively with our clients to ensure the successful and sustainable delivery of projects. We also firm believers in knowledge sharing, and this is why we're here with you today. Today's session will be presented by David Van Bergen, who is a senior power engineer with this Middleton Group. And today's presentation will run for approximately 30 minutes with the remaining time open for questions. As always, just some quick conference room housekeeping before we begin. Can I please ask everyone to keep your microphones on mute unless speaking or have an urgent question. Alternatively, place your questions in the chat and we'll be able to get to them during question time. At the end of the presentation, I'll post a short survey link which will help us bring more interesting presentations in the future. So thanks for your time, and over to you, David.
Cool, thanks Jack. Thanks for the intro. Hi everyone, good afternoon. Welcome to the presentation. This is really part 2 and continues on from the first presentation I gave about a month and a half ago on an introduction to secondary design. So in terms of what we'll cover in the 30-minute presentation, I'll do a quick recap of the first masterclass, Introduction to Secondary Design. We'll then run through a case study, which will be the bulk of our time this afternoon. And then, as Jack alluded to, we'll have question and answers. So feel free to jump in if you have a question as we go through. Okay, so what is secondary design? So as we covered off in the introductory presentation, secondary design covers as a minimum the electrical, automation, communication design required for the deployment of secondary systems in an electrical network. So that's a very elaborate means of saying we have primary plant or assets, and what we want to do via the secondary design is connect that via a medium, which is generally copper cables, as you can see here in various forms, to a means of whether you can enable the control of that said plant via local or remote operation. So at a very high level, that's effectively secondary design. The way that is captured is through a whole lot of schematics and diagrams, as well as wiring tables, connection schedules. There's various means and forms that the panel representations can be made. So it depends on the type of site that you have and the type of plant that you're replacing. Some, if we talk about a terminal station for a utility, for example, a 220 to 66 kV terminal station with say 5 transformers, you're probably looking at a couple of thousand drawings in the secondary realm for that site. Depends on the vintage and the type of site. The most I've ever worked on in terms of one particular project, which was a complete brownfield upgrade from AIS, so air insulated switchgear, to gas insulated switchgear, had about 20,000 drawings. So that was a massive undertaking. So effectively the schematic drawing that we just had on the previous slide, this is a representation of what it might look like in the real world. And secondary design can often be lost, excuse me, lost in translation. And that loss is really down to communication. And it helps a lot, particularly when you're a younger engineer starting in the secondary field, to visit lots of sites, to have a look at what equipment is installed at that site, and that gives a greater appreciation for what is in the drawing. So at the end of the day, it's not a drawing. The drawing is just a representation, it's the equipment and interfaces that really matter. So I've just shown a couple of comms or SCADA connections, and that's just a bit of a roundup. A couple of drawings, sorry, a couple of photos of DC batteries, which are used for supplying IEDs or intelligent electronic devices as part of your plant. And on the right, we have a switchboard. Right, so that's the completion of the recap from the first presentation. Now, the crux of this particular topic is delving into a case study and approaching that from a secondary point of view in delivering everything from the initial concept right through to construction support. So let's go into that now. Okay, so we have an imaginary scope, which I've just put together here. And that scope for our particular case study is the replacement of two 150 MVA 220 to 11 kV or via 6 kV winding transformer, installation of new X and Y or A and B, depends on what terminology you'd like to use for redundant protection schemes, transformer protection, installation of new 66 kV circuit breaker management schemes, and they are on the secondary side of those power transformers. So that, in essence, is our scope, combined with the removal of the existing and redundant equipment. So that's a fairly straightforward, I wouldn't say straightforward, but in some circumstances, it can be quite tricky, but this is just a general secondary scope that we'll use for our example. So hopefully that all makes sense in terms of what we're doing from words. I'm going to now translate that into physical appearance via some drawings. So that's our scope. What would you do next? And this is really the planning and developmental side of the project and how we would actually complete our planning to then deliver the solution. So a few steps and an approach that we could take for this. It all starts with the high-level overview drawings, the single line diagram, the protection single line diagram, the site layout, the control layout. It gives a feel for what we're trying to achieve. So we're looking at replacing two transformers, which means there's a transformer protection panel. There might be X and Y, so each scheme might be in a separate panel. They might be together. There might be a tap changer scheme or something similar that we need to look at as well. There are circuit breaker management schemes, which may or may not be there at this present time. We need to have a look into it. And to do that, we start with the high-level drawings. We look at our site, the conditions of the site. We look at our control room layout, and then it goes from there. So that's really step one, is to gain an appreciation of the scope. We need some information of what we're trying to do. The second part is to then, once we have that understanding, is to identify the standards that we will be implementing and then establish principles of the design. So that's really client standards, Australian, New Zealand, local, whatever is required. But then also there might be certain requirements. For example, instead of using space in the existing control room in a certain allocation, there might be an extension to that building, and we might be putting panels in a new location. And for that, there's a whole, there's quite a few other factors which we might need to consider. Confirm the scope and interfaces. So just because we have a scope doesn't mean that the scope is necessarily 100% correct. We actually might find that as we're part way through the design, that there are a couple of things that might need to change. The scope might be increased. There might be additional changes which might need to be made, and we might find that interfaces don't quite align. So we really need to understand and confirm our understanding of the scope with what is at site, with what our drawings convey in terms of the information, and then pull that all together. So in essence, what I just described is planning. So the key to project success is all about the planning and keeping that plan live, and also communicating that to the team and everyone involved. Without a plan, it's very easy to go off track and get sidetracked in terms of delivering a project, particularly when there's tight timeframes for the delivery and interfacing to particular disciplines within that project. In our case, we have two disciplines, which I'll talk about today. There might be others, depends on the scenario, but today we'll talk about structural and primary and how we interface to those elements for the transformer installation. Yep, once we've done our interdiscipline coordination and we have an alignment on what needs to be done from a secondary perspective, we then complete our design and take that right through to the construction phase and support. So that, as a high level snapshot, is what we will do for this particular case study. So if there's no questions, we'll jump straight into it. And that's the first point. So that's identifying the scope and interfaces. So here I've just pulled up a random SLD, not quite so random, because we can see down here in this clouded area, we have two transformers, which are 220 to 66 to 11 kV, which are highlighted or clouded. And that generally means that we are changing or modifying this particular drawing to replace that equipment. So in our case, we're replacing two transformers, which are connected into these bays here. We are then connecting the secondary sides through to number 2 and number 1 66 kV buses. So right away we're thinking, okay, as well as replacing the circuit breaker management schemes, we will also be looking at interfacing any CTs into that bus protection scheme. So straight away we've got a greater appreciation of what may need to happen. So from the single line diagram, we jump into a lot more detail. So we've now found our protection single line diagram. This is on the 66 kV side, and that really details our current transformers and where they sit in terms of the transformer. They may be internal to the bushings of the transformer. They may be external in the form of neutral CTs, which may be procured separately from the transformer, but may be required to be specified, and they might be for restricted earth fault protection, which we can see here, going into the transformer differential box, which is really our relay. So this drawing is a representation of what current and voltage we are passing into our particular relays that we'll be installing or replacing as part of this project. So from this drawing, we now know, right, we've got this number of CTs, basically. We've got a couple of NER neutral CTs. We've got on the secondary side, a couple on the primary side, which will go up to the 220 kV equivalent drawing that shows interfaces and interconnections. Moving down from the transformer protection, you can see here we've got duplicate circuit breaker management schemes, and they're really used for monitoring and controlling that 66 kV breaker, but also performing CV fail, circuit breaker failure. So that's part of any requirements. That's number one. That's the first transformer. The second is quite similar, but a little bit different. So we've still got a circuit breaker management scheme, but there's not duplicate. There's only one. So that may indicate that this particular site may have had a recent refurbishment not too many years ago, and instead of replacing the second circuit breaker management scheme, it might be a single scheme, and there might be a second scheme that we have currently within the transformer prot. So that transformer protection, sorry. So it depends on the scenario. So while it sounded like it was quite a similar arrangement, it might be quite different. So straight away, we've got an even greater appreciation of the scope based on glancing at a couple of drawings and spending 5 minutes to analyze what's going on. All right, now we've had our we've looked at our high level drawings. We understand the scope a little bit better. Next step is, right, okay, so what are we going to do? So we've got transform protection, we've got circuit breaker management schemes. What are they going to be based off? Are they going to be based off client standards? Are there particular templates that might need to be used? Are there other examples from other sites which may be used as a sample, which we can take and implement? Always going to be a completely new scheme, and we're developing a brand new standard based on certain client requirements. So that's something that we'll need to understand. Compliance with Australian New Zealand standards, depending on where you are and how that interfaces, AS 3000, AS 2067, etc. Are there any specific design requirements which may not be necessarily known up front, and that might be operational or maintenance requirements on equipment, plants, the choice of equipment, the height of the equipment, for example, within a panel. Is it meant to be between 600 mil from the ground and no higher than 1.5? These sorts of things we need to understand. And largely, if the client has a standard, it will be contained in there, but if not, then we need to flesh out that detail. All right, so we've stepped through the drawings, we've had a look at our standards, we have a rough idea of what we need to do. The next part is to confirm the scope, lock it down, and work through the interfaces. Now those interfaces can include identifying on the site within the control room where those panels will be situated. That's the new panels. Where the existing panels are currently located. Can we do an in situ replacement? What type of panels are going to be? Will it be a swing frame? Will it be an SF insert? So that there's an existing panel arrangement or racking arrangement, and that's just the new panel is going to insert in. Is it going to be a freestanding panel? That's quite a big, because that has quite a big implication on the design, where the cables will run, what type of cable trays will be used, cable ladders, etc., etc. So that's really a key point that we need to lock down. Assessing the existing auxiliary equipment. So we'll go through this in a little bit more detail, because this is quite a key one. So even though our scope says replacing transformer protection and installing new circuit breaker management, we really need the functions existing to the site to be able to help us with that. So what I'm talking about here is, are there enough DC MCBs within our DC distribution panel on the site to provide the supplies to our new panels? Are there sufficient AC supplies? Have we done a check of our battery loading on site? Will the battery be overloaded with our additional load? Is the AC system sized okay? Do any of this, do we need to install new MCBs? These are the type of questions that can easily arise when assessing the interfaces. And that continues on through to SCADA system, the number of cards within the RTU. Do we need an additional card? What type of card? Is it going to be hardwired points? Would simply be a DMP3 connection to a relay? What type of connection is required for the relay? Each manufacturer might have a different arrangement. It might be DMP3 over Ethernet. It might be, yeah, we just need to arrange and confirm what's there in terms of those auxiliary systems. And the same goes with the next part, which is confirming locations. So we talked about panel locations, but what about cable runs? Are there interface locations for the field cables, which go into the control room? Do the field cables run directly to the existing panel? Do we have an interface or cable termination cubicle? Where will that be? How's that situated in relation to the existing panel, to the new panel? What space is available? How can we make it all work? Now, once we've done these basic self-assessments, I would call them, or basic confirmation of the design requirements, then need to confirm everything we've found from our drawings with what is actually on site. And this is quite an important step, is undertaking a site visit up front, once you've got a basic understanding, to then confirm everything that we understood. Go through it with the client or the customer or our own internal team, depends which design team you're sitting within. And then once everything's okay, then you can go and proceed with the next stage of the design. But that site visit is really a crucial step, because you might find that when you undertake the site visit, you're looking at your DC distribution panel, and this often happens, and you might look at the drawing and say, right, we've got 3 MCBs free. That's excellent. We're going to use 2 for our transformer, and we'll have 1 for our circuit breaker management scheme. And then the other circuit breaker management schemes, we might use a different distribution panel. But then when we go to site, we might look at that panel and go, oh, right, actually, there's actually none available. They're all taken, which means we need to actually use another panel, which is over there, but they don't have enough MCBs. Okay, easy. We'll just install a couple as part of our bill of materials and get that sorted. So that's really, and then we then go back and look at the drawing and go, right, we need to actually mark that up. We need to confirm that this is not a true reflection of what is on site. So that's something that's quite easily overmissed, but very crucial. Okay, so I talked about, so I've been doing a lot of talking. I would like to show a couple of drawings. So this is a general example of a control room. The way these panels are represented here is the probably oldest style 60s, 70s of the panel frames, where you have one common frame throughout that area, and you've got panels mounted in on each side. This is fairly typical, and when you want to replace or install a new panel within one of these available slots, you would use what's called an SF insert panel. It's a bit smaller in terms of dimensions, but that panel would effectively slip into the existing frame and then be supported by that existing frame. When you look on the right over here, the way these panels are represented are generally freestanding. So they're full cubical height and width, and they would be, as they are called, freestanding. So they would be just bolted to the ground, earth straps between each panel in two locations, just for the continuity of that earthing arrangement. And then you might find that you have cable trays over top with this particular arrangement, while with the frame type arrangement, you might find that the cable access is underneath rather than on top. So it's a different arrangement. Again, it depends on the vintage of the site. You may have cable trays on top, but that's, yeah, depending on site requirements. So from here, I haven't highlighted where the existing transformer protection panels are located or where the existing circuit breaker management panels are located, but we could easily look at our schedule for the control room and say, right, 13 and 14 is where those panels, the existing transformer panels, are located, and we may have been asked as part of the scope to put the panels in locations 1 and 2, the new ones, or 124, 125 if they're free. So straight away we've got to recognize, okay, where are the cables where the existing field cables marshaled for this location? Are they in CTC A? Are they in CTC 2? Will there be a changeover? Are there any signals which we need to keep as part of the existing arrangement? For example, there might be an on-load tap changer scheme. There might be another scheme that we may need to interface to for the transformer, like an auto close scheme. There's various things that we need to consider for that. I might just move on to the next slide. So with those ITCs or CTC drawings, we just talked through, this is a representation of what they actually look like in the 3 forms. So physically outside the control room, so you can see the panels situated here with doors. So each, I think it's each 6 doors is 1 panel or 1 CTC from memory. What it looks like from the internal in terms of cables running in, cables running out, and typically you'd have field cables on one side, cables that run into the control room within another side, and again you'd split that via redundancy, so you might have an X and a Y strip, depends on what's happening. And then that on the left is how it translates to drawing form. So this is an old raster style drawing, but it has terminal strip number 2, cables going into the panel, and then field cables. So that's the 3 forms that we generally look for. So you would so you'd start with the drawing, take photos of what's actually there. Do they marry up? Do they all match? Great, excellent. Whereas the free terminals, can we use them? That's all part of the design considerations and confirming our scope. Another part which sometimes can get overlooked is the cable trenching arrangement and how cables will need to be run between the plant. So for example, the 2 transformers that we may need to install to the control room, which is down here. So those CTC or ITC interface boxes, which we just looked at, are situated down in this bottom right-hand corner of the control room. So we need to actually confirm, are there existing trenching arrangements in place? Will our project install additional? Are the trenches full? The segregation in the trenches, is it all looking okay? How will the cables get from the transformers to the control room? And straight away from this nice Google Earth shot here, we can see that there's existing cable trenches which run over here to the building on that side. And there's also one on this side up here. That's actually going to the other control room. So there is a path. We just need to confirm if it's actually full or if it's in good condition, or if we need to actually install something new. And that might be an extension, or it might be okay. And that's really confirmed during the site visit and based on an estimate of the number of cables that we will need to install. And that also feeds into one other part, which is the voltage drop calculations and confirming the cable run. So we'll need to calculate the distance that the cables will need to run between, say, the transformer, the 66 kV circuit breakers for circuit breaker management schemes to the control room. And then we might find that it's all okay in general cases, but we need to confirm that as part of good design principles. Right, so now we've gone through and understood a bit more about our scope. We've looked at our high-level drawings. We've got a bit of a plan based on our client standards and how we're going to approach this. The next part is really bringing all of that together. So that's really planning the design works. And that planning can come in multiple forms. Generally, you'd start with timeframes for delivery and see when certain aspects of the design need to be delivered, what interfaces there will be. So for example, will there be a 30%, 80%, and 100% issue? So that can be called or considered concept, detailed, and for construction. What is the resources allocated? So am I going to do this by myself? Will there be a couple of internal people that can help with this? Who's doing the primary scope work? Who's doing the secondary, the structural and the civil? What inputs do they require at certain times? Do we have the same time frame, et cetera, et cetera? So that's the key to the plan, is to make it in the first instance, keep it live and continually update it. And then whoever the team is and whoever you're working with, keep them informed. So make sure you communicate exactly what you're doing, what you expect from them, gather from them if they're not being too clear, gather from them when you need to give them inputs by, and vice versa, and just keep everything on the same footing. And without that planning, it makes it very hard to deliver the project. And that planning, to actually recognize what comes from where, for example, the secondary interfaces with primary and structural civil, we actually need to understand how that coordination and planning works with the other disciplines. So with primary, structural civil design, are there any others? I'll be replacing parts of the building. Will there be any HVAC upgrades or changes? Will there be any building services? Are we installing new switchyard lighting? Do we need to do a lighting study? Do we need to reassess our lightning protection and install maybe some new poles or posts based on standard or the rolling sphere method? Other considerations. Because if we do go down the path of installing new lights and maybe even CCTV or security, we need to run cables, and then we need to have power supplies for those, and et cetera, and that would be covered as part of our secondary domain. So really those interfaces and interactions need to be planned, and we need to lock down a time frame for us to actually do that. So key inputs: what time, when, what form. Okay, so let's jump onto our primary design. So some considerations we might need to consider is the marshalling boxes for the transformers. So they might have a secondary marshalling box in, if it's a different transformer, where they're located, what type of, how many cables do we need from those marshalling boxes, what number of cables, are we going to use conduits? If so, what size conduits? We'll have to do some calculations around that. And it keeps some fill available, because there's no point, and it's very hard to pull off a conduit which is full of cables. You need to have some space availability there and some capacity in order to pull it. That comes down to an installation point. So that's general primary considerations. CTs, how many neutral CTs are required? Are they external? Are the transformers, current transformers within the bushings of the main transformer? How are cables going to come from those, et cetera, et cetera. So we need to look at the plant, identify where things will run from, where they're situated, and then interface with the primary team to then effectively make it happen. And the same goes with structural and civil. So structural, civil, and primary have a very close relationship, particularly for equipment replacement or plant replacement. The key interface with structural and civil and secondary is really around those conduits and confirming where the conduits will run, particularly around the transformer bund, concrete requirements, et cetera, et cetera. Secondary doesn't touch any of that, but we just need to know where the conduits will be and the number of those and make sure it's sufficient. And then the other thing we need to actually look at is within the control room, will there be cable trays required? Are there cable ladders required? Do we need additional trenches in the field somewhere? What size that will be, etc. So the structural design really comes into those particular items for this example. So once we've done our planning and coordinating, we can take a deep breath. And then after taking that deep breath, we can then jump into the design. So we've done our plan, we understand our scope, we understand our interfaces, we've locked it all down. We've spoken and interacted with whoever the stakeholders are on the project, so they're aware of what is happening, what we've found from our site visits, and all of our information is correct and we're good to proceed. And once that's all done, we can then dive into the design. So it takes a bit of time to get here, but really that planning up front and nutting out all the issues makes the design phase a lot smoother and saves everyone a lot of heartache down in the construction, installation, testing regime. So some typical design elements that we might look to do straight up is to confirm the relay order codes and firmware for the relays that we're using. Generally, relays are long lead time items. Depending on the manufacturer, it might be 8 to 12 weeks or even longer if they're not, if they're a custom order, or it depends where they're located. So we really want to get that confirmed and locked down up front and make sure that we get our order in. We then look at our schematics, drawings, cable connection schedules, cable termination schedules. They can take different forms, but effectively each piece of equipment will have a list of terminals, what's going into those terminals. Wiring diagrams, likewise. Wiring diagrams and schematics are very different. So schematics and wiring is more physical, how it's physically wired. Schematics is more holistic. So they're different things, but depends again on what we're trying to achieve. And then configuration files for the relays themselves. That's also a design outcome, and that's based on the logic that we need to then implement within the relay. Could be standard, might not be standard. We need to get those files, do the set points, do our load flow analysis, calculate our protection settings, and then go from there. So we can do all that as part of the design. And then, point I mentioned earlier, the bill of materials. So I kind of flashed through some of those items. But if you looked at it from a schematic point of view, this is what we'd be doing. This is very typical for a secondary design. You just keep pumping out schematics, and the schematics can take very different forms. There's a lot of secondary can be translated to a bit of, I can call it a bit of an adventure, if I can call it like that. You need to do a lot of detective work. If you're tracing an old signal, which might not be referenced on one drawing, which may be shown somewhere else, there's generally another drawing at that site somewhere that shows the information you need. And your job is to try and find it. So it takes a lot of digging, a lot of searching. Once you find it, and then you can relate to it and confirm it from site, it makes a whole lot of, it just reduces a whole lot of problems, but it also is quite rewarding, I would say, for someone who's doing the design to actually go and find things that are hard to find. That's one of the things that I enjoy anyway. So panel, as part of our design, we've now done a couple of panels for our transformer, for our circuit breaker management. We've looked at our DC distribution and gone, yes, we've got a few free spots there, and we've got quite a lot of available space in that third rack. So we'll install a couple of MCBs for us. That's great. Our batteries, we've done our quick loading calc and everything's okay. We're not going to overload those batteries. Excellent. Let's move on. Okay, SCADA, digital interface cubicle for engineering access. We've got ports available. We'll connect up those ports, update those drawings, make sure everything's okay, assign some IP addresses. We can then do our mapping table, which is really mapping out all the individual control and monitoring points and status points within the relay to SCADA. So we've got all of those addressed, indexed, and ready for the SCADA system. And then we can jump into our configuration files. So jump into whatever software we're using, have a look at it, put our set, once we've done all of our fault calculations and our CT adequacy calculations, etc., we can then calculate our set points and then program them into the relay along with any logic. And of course, once we've completed a certain stage of our design, we then need to jump into, which is a fairly critical part of the design process, is safety in design and constructability. So we would generally look at holding those at each stage. So the 30%, 80%, and 30%, 80% part of the design lifecycle. And we would jump into safety and design, jump into constructability workshops. The key to that, to those two workshops, is having the right people in the room. We need to have the operational, the maintenance, the right stakeholders. If we have the correct stakeholders and they're all available and engaged, then we generally deliver a good outcome, because you have the right people talking about the issues, solving the issues, and then either changing and modifying the design by eliminating potential risks or identified risks. And if not, then closing that out by passing on those residual risks to the client for management. And that's really following the hierarchy of controls. So elimination at the top or the bottom, that's number one. And then I think PPE was the last part. So update our design based on feedback from those workshops, any comments, preferences, etc. And once we've done that, we can then issue it. So we've done our design, we've done our workshops, we've had everything signed off, we've had the right inputs. We can then issue our design and follow it through to the next stage. So at this point, we have another breather. We can relax for maybe 5 minutes or so, and then we jump into the next part, which is confirming that all the right parts have been ordered, it's all been delivered to site, we have the right construction support in place. That might be the right people attending site at certain stages, working with the contractor, or if it's an internal team, having the right person who's familiar with the design and is the best person for there. But then also bringing in a training aspect. So can we train someone or bring someone along to learn a bit more about construction methodology, the processes, and take that back to further their career? And that's quite an important one. As well as assisting with queries, being on site as much as possible. And the last step there is as-build drawings. So as-building and closing out the design based on feedback. So there might be something that we've done in our design, which when it actually came to the construction or implementation side, we couldn't actually run that cable from there to there, or there's something else that's there that wasn't identified. How do we fix that? Okay, we can possibly do this, this, and this. So then we need to mark up our drawings, make sure that we've got it reflected correctly. Once that's done, we can then reissue our drawings at the end based on as building or as built. So as the site was left at the end is what's reflected in the drawings. And then closing that out with feedback. So feedback from the construction team, the installation team, but then ultimately whoever's the stakeholder or key stakeholder on the project. Okay, so I've just really blasted through a lot of those slides, but in summary, we went through a brief review of the first masterclass session, which was on an introduction to secondary design. And then in this one, we've completed a secondary design case study. So well done everyone, we've flown through it in half an hour. It was really, really quick, but at a high level snapshot, that's exactly what we're trying to do from a secondary point of view. And they're generally the steps that we would follow in order to implement that design. And that's it.
Thanks, David. Another great presentation. So if you've got any questions now, feel free to chuck them in the chat or come off mute and speak to Dave directly. Yeah, fire away if you're ready. Might have been too comprehensive, Dave.
Maybe too much information.
That was great.
Trying trying to pack a lot in there. I mean, yeah, if there's any questions or anything even related to secondary design, happy to, or any feedback if that was too much information, or there's any items that there might be a bit more of a focus on that you'd like to hear a bit more on, we can also cover that off.
If not, Dave's email's there, and you can get my email through the site, and feel free to send me an email. Just got a quick one, Dave. Can you see the one from Eugene in the chat there?
I can. Okay, so Eugene, in terms of the number of projects, I was fortunate to have worked on quite a number of larger projects earlier in my career, well, not early in my career, but when I started in the secondary design space. So each project ran for about 4 or 5 months, and they overlapped. They happened to be at the same site, but just replacing different equipment. So for that, probably a year, and that was maybe 3 or 4 designs until, and a lot of site visits and a lot of feedback from panel constructors from site until I felt comfortable with what I was doing. And that's actually the interesting point about the feedback is when you do something in the design world, like if you do, for example, test links or terminal links, and you accidentally renumbered links the same numbers, you cop a bit of heat when you go to the panel constructor, and they're quite good at pointing out how they would improve the design and how you've been not so good in doing these things. And that's when you really learn a lot and you don't forget those particular lessons. And that's probably the real benefit of our industry, is that everyone's been quite open to providing feedback and also their knowledge. Okay, so a couple of other questions. Okay, so from Omar, do we usually use some of existing cables when we replace transformers, save space and trenches, or just everything new? Okay, so it depends on the client standards and the requirements. So you could end up using the existing cabling if it was found to be in good condition, and if we had enough cores for what we had to do with the new protection. But generally, you would actually run new cables, and it's a lot easier for the site team to actually run new cables. And then that way, because you probably end up finding that you need to run new cables anyway, but so from the field, from the transformer itself, you would run the new cables, but within the control room, you may end up using some of the existing cabling if the panel is located next door to the existing or close by. If it's in a different part of the room or in a different panel row within the control room, then you would actually end up just running a new cable, because you can't physically pull it from that location to be in that other panel row. It's so that's generally everything is quite new. Okay, no worries. I think you're on mute there, Jack.
I think I'll be good at it by now. So yeah, if you have any other questions, like I said, you can reach Dave. His email's on display there, and my one is attached to the presentation link. So feel free to reach out to us, and I'll also share the presentation around after to those who attended. So yeah, thanks again for everyone for coming, and thanks David, another great presentation. Keep an eye out. We have another masterclass coming up next week. Look forward to seeing you all then. So thanks again. Thanks guys.
Cheers. Thanks, Jack. Thanks all. And even if you have a general question about anything really, feel free to let me know. Happy to help.